So welcome everybody to our, like I was mentioning to you guys, we haven't done too many of these, but we're really excited to probably do more of these. So welcome to our winners webinar. My name is Cal Sahota. I'm the VP of Possibilities with the HeroX team. And we're pleased and excited to be hosting our Exploring Hell Winners webinar. I know the name is that's just half the fun. Kyla, you'll have to tell us maybe in part of your share as to how you came up with that name. So what's a winners webinar all about and what's in it for you? Well, how about you get a chance to learn exactly how NASA leveraged crowdsourcing to solve issues with exploring the surface of the planet Venus. Pretty cool stuff. So we're excited to share some of the amazing stories which, if you're new to crowdsourcing, will hopefully inspire your creativity and likely compel you to view the simple act of solution finding in new and actually powerful ways. So we have a few guests at our party today. So how about we start just with a quick round of introductions. So joining me from our HeroX team, we have our very own CEO and co-founder, Christian Cottagini. Hey, Christian.
Hello. Hi, everybody.
You want to take 30 seconds and just share a little bit about this is who I am and why I wanted to take time out to join today?
For sure, yeah. So, we founded HeroX on the premise that, if we work together, anything is possible using the power of the crowd, which is really the power of humans. We're all 2 clicks away from each other, and many organizations are still stuck in this building mindset of, we'll just work on our problems in our office and in front of whiteboard with people that we have that have to come to the meeting because we're paying them, and ignoring the amazing, unbelievable talent that's out there in the world. And many of the creative, innovative people out there see all of these problems and these opportunities in the world, and they'd love to participate. And so the beauty of crowdsourcing is it opens it up to anybody who wants to solve a problem. Anybody who wants to work on a NASA project can do so. And so we just see this as a huge next step for the development of us as a society, and just accelerating, tackling the problems that the world's facing, and helping leading organizations like NASA pave the way and doing some amazing work using the power of the crowd. I'm very excited to be here.
Wonderful. Thanks so much, Christian. And we also have here with us our Director of Challenge Success, who was also our project manager for this project. So Kyla's, for those of you who know Wizard of Oz, she was the person behind the curtain doing all this extra stuff that nobody could see. So Kyla, why don't you share a little bit about who you are, and in your share, you gotta tell us, how did you come up with a name?
Sure, absolutely. Hi, everyone. It's a pleasure to meet you. My name's Kyla Jeffrey. I'm based in Vancouver, Canada. And like Cal said, I've had the pleasure of working with Jonathan and Ryan from the very start of this project, forming what the challenge looks like and the guidelines, all the way to seeing the winning solutions. And it's always so rewarding to see all of the amazing effort that goes into these challenges from not only the winners here, but everyone else that participated and submitted an entry. There was an incredible amount of participation and just quality teams and innovators that came from this project. The Exploring Hell Challenge, I would be remiss if I didn't give that credit to Jonathan Yakasha, who was the challenge designer, who I believe was the one that came up with Exploring Hell. And if you know anything about Venus, you know it's a rather hellish environment, which I'm sure Jonathan Sauter, who's on this call, could maybe tell us a little bit more about, but certainly is a accurate name for the types of places that we're trying to send these rovers to.
Wonderful. Thanks for joining us today. And I'm sure it's exciting for you to kind of bring all of this full circle. So, and of course we have our NASA team with us today, Jonathan Sauter and Ryan Stewart. So gentlemen, we're going to hear a lot of chatting about this great project and all these wonderful solutions. How about you tell us a little bit about who you guys are? So let's see, who can I pick on first? Jonathan, you want to go first?
Hello, my name is Jonathan Sutter. I'm the challenge owner and also principal investigator on the Automaton rover for Extreme Environments project. And my background is actually in mechanical engineering, but also design theory and methodology, and trying to understand how do we get the best ideas out of collaboration in design was what my PhD was on. So it's been wonderful to see that executed here in this HeroX challenge and see the amazing results that we've gotten out of this challenge. So.
Wonderful to have you here. And Jonathan, where are you located? Are you in Houston?
So I'm located in Pasadena, California. So.
Pasadena, California. Wonderful. A little bit warmer, I'm sure. All right, great. Well, thanks for being here with us today. And Ryan, how are you this morning?
Oh, I'm well. I'm in Houston, actually. So yeah, I'm in Houston, Texas. So my background is in aerospace engineering, and my role here was as the challenge coordinator. And so my office functions as a way to try to help utilize crowdsourcing to get good solutions for NASA. And so if you're familiar with the NASA Tournament Lab, as is branded on HeroX challenge page, my group runs that NASA Tournament Lab. And so we understand the power of the crowd. We understand the power of getting really good solutions from all of you. And we go to people like Jonathan to help get their solutions from the external community. So it's really, really nice. Real quick, my background, before being in this route, I was a flight controller and instructor for the International Space Station. So I was flying the space station and teaching astronauts about how to do it. But now I find myself here. It's very exciting.
So cool. I don't think there's very many people that can say that. Thanks so very much for joining us today, Ryan. And he has a great team. We work really close with him. We're coming on to the 6th year of working with Ryan and his team. So really exciting stuff. All right, guys, so how about we do the winners introductions now? So a really quick note, there are 5 winners, but 2 of the winners are teams. So there's going to be actually 7 introductions. The one thing I want you guys to really be present to, and I say this to the audience, is you'll hear us say at HeroX oftentimes that genius can live anywhere. And you're going to hear as part of their introductions, not only who they are, and obviously what compelled them to compete, but lastly, where they're located. So, you know, you'll get a sense and feel of all the different areas that they're from. So, all right, so let's start with, let's do the teams first. So Martin and Eric, do you guys want to go first?
Yeah, sure. Eric, do you want to go?
Sure. So I'm Eric Seeberger. I'm from Los Angeles, California. And I initially found out about this challenge, I think, on an article on NASA's subreddit page. And I reached out to Martin about it because we had worked together on a lot of projects when we were in school, and we always worked well together. I thought this was like a unique challenge that kind of played to our strengths as mechanical engineers. And I was kind of excited to see how we would stack up in like a open competition like this.
I'm Martin Grabow. I'm currently living in Santa Barbara, and Eric and I went to UCSB, so I didn't make it too far after graduating. But yeah, like you said, we did a few projects together in college, and we've done a few since graduating as well, but never anything like too serious. So, and we've both always been really interested in the stuff that NASA does and aerospace in general. So we thought that this would be a really awesome opportunity to put our teamwork towards something really impactful.
Wonderful. Well, welcome both. Next team, we have Christine and Oscars.
Hi.
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 Hey.
We are COBAR team. We are located in Riga, Latvia. This is Oscars. I'm Christina. We are actually a team not only in business but also in life. we are married as well, and our everyday work is mostly connected to a different form of art and technologies. But we as a company have never defined any boundaries regarding what we do.
Yes, that's true. When we found out about this challenge, it compelled us by its format, because it's invited to design something simple and mechanical, and we love to use different technologies and solutions to make our ideas come to life. This project was a challenge for us, but it was a really, really great experience.
Yeah.
Thank you.
You're welcome. And there's also a baby behind them. So, you know, at some point you might hear a baby crying. That's
actually, if I can say some secret, our solution is called AMI sensor. And our baby is called, her nickname is Ami. So that's the story.
Beautiful story. I love that. All right. So, Yousef, you want to go next?
Hi, hello everyone. I'm Yousef Gali, an architect and product designer from Cairo, Egypt. What intrigued me to join the challenge was that I fell in love with the concept from the first time. The concept of building a mechanical rover that works with mechanical computers to be able to overcome the hellish conditions on Venus. That sounded very strange to me at first, but the more I read about it, the more I realized how practical that was. That kind of problem solving is, I'm very attracted to that kind of design approaches. Thank you.
Wonderful. Thanks for being here, Yousef. And let's move into Callum.
Hi, everybody. My name's Callum. I'm coming to you from a cold, dark, early morning in Brisbane, Australia. I entered the competition basically because I love mechanisms and pretty much everything NASA does. And as all the others have said, yeah, it's a very interesting and rare problem that focuses heavily on mechanical design. So I just couldn't resist.
Wonderful. Well, welcome. Clear across the world. Let's see. I think Matthew, you are last, but certainly not least.
Good morning, afternoon, evening, or night to everyone out there. I'm Matt Reynolds, a design engineer based in York in the UK, and my submission was called Echoes, but more on that later. My career to date has been in mechanical engineering, contracting, which has given me lots of opportunities to tackle problems in lots of different industries, but unsurprisingly, those have all been firmly based down here on Earth. So when I found out about the Surviving Hell Challenge, my mind was immediately buzzing with ideas and my hand reaching for a pencil. So there wasn't really very much question about whether I'd be entering or not.
Great, wonderful. And once again, welcome to everybody. I think I've gotten everybody. It's a full house today. Listen to our audience. If you have any questions that show up for you, please drop them into the chat. And if the questions are for any specific panelist, you can just please make sure that you note that who they're for. If we have a bit of time at the end, we'll try to address the questions. If not, we can certainly do that offline. So, okay, so Jonathan, tell us a little bit more about the project itself.
Absolutely. So I thought I'd actually start out with a very brief sort of slide presentation here. So
go for it.
Let me go ahead and hit share here. So you should be able to see my screen now, I believe. So the concept is called Hybrid Automaton Rover Venus. And the idea is that when we look at Venus and the surface of Venus, it's 462 degrees Celsius, extremely hot, above the temperatures of where paper spontaneously combusts. And most electronics and a lot of solders will melt at those temperatures. There are some high temperature electronics made out of silicon carbide and gallium nitride, but they're limited to about the capability of a solar powered calculator. So you can't do very much with it. And when you compare, what we've used traditionally for rovers on Mars and look at using that for Venus, there's really no way that you could design a current rover to operate in the Venus environment. It just doesn't work. So you have to go back and completely re-envision what a rover looks like. And that's where we came up with the hybrid automaton rover concept for Venus, a mechanical wind-driven rover that drives across the surface of Venus, would have some simple high-temperature electronics on it for science instruments. But the idea is that most of the mobility and system is mechanical. And for that, we needed to figure out a specific way of detecting obstacles on Venus. Traditionally what we use with like the Mars Perseverance rover, which is launching next week, is we use image recognition sensors and image processing, but that requires really advanced electronics. You can imagine you really can't do that if you have the electronic capabilities of a solar powered calculator. So we needed to come up with something that was more basic and would work in the high temperature environments with the limited capabilities that we have. The other key challenge with Venus is that Venus has a very long night. In fact, night is 60 days long because the planet rotates so slowly. Therefore, once again, you can't really get good images of the planet. So you have to do short range obstacle detection. And so we were looking for a manual approach to detect obstacles, namely holes, rocks, and slopes. And we're thinking the idea could be maybe bumpers or wheels or sonar or something else. But if you're going to fly a rover to Venus, because of that long night and because of the high temperatures, you need to be able to have something to detect obstacles at a short range aspect for mobility. So that had us create the Exploring Hell Challenge. And the key challenge here was to detect slopes that are greater than 30 degrees and slopes less than 25 degrees should be ignored. Detect rocks that are greater than 0.35 meters tall. Rocks less than 0.3 meters in height should be ignored. And then also holes and valleys that are greater than 0.35 meters deep. And then also, but ignoring those that are less than 0.3 meters deep. And there's some additional conditions here that holes that are less than 0.5 meters long can be ignored, but it's not required to do so. But it has to detect all holes that are greater than 0.5 meters long in the direction of travel of the rover. So that's a challenge that we put out there. The holes and valleys by far were the most challenging, I think, of this as the challenge developed and as people provided feedback in the challenge. But we got an absolutely amazing set of solutions from the winners that you're going to hear today and hear how they solve those challenges. And I think one of the things that's really innovative about the solutions that you hear today that really made these winners stand out is, one, the incredible level of detail that they put into these challenges. And secondly was the approach for avoiding jam conditions. The holes turned out to be a really challenging aspect to make it so your sensors would not jam. And each of these had great ideas for how to avoid those cases.
Wonderful. Thanks for that overview. And so tell me, I'm going to ask you the all-important question. How did this compare to your experience of using competition versus the typical route of product design?
So the typical route of design at JPL is we would have designed one sensor by brute force, and probably would have been someone asked me, what was sort of the initial idea that we had in front, as the initial concept. And we probably would have come up with some type of wheel that's, rolls in front of it and basically would sort of drop down into holes or go up over rocks. But there's challenges with that, and especially meeting the, detecting holes that are 0.5 meters long or greater. If you were to design a wheel that could make its way out of holes, that probably would not have worked so well. What was incredible here is to get 5 different architectures that are all different, right, that have unique ways of finding the same challenge and have a diversity of approaches to all solve this issue. And that was amazing. And to get the level of detail, we would have just taken one specific concept and would have been sort of limited later on as we would proceed to prototyping and testing if one wouldn't work. In this case, we now have 5 different potential solutions that we can start with building and prototyping one, and then if things don't work, we can either incorporate aspects from some of the other solutions or switch to another architecture that we have as a backup. So it's wonderful to have all these amazing options in the solution trade space.
Wonderful. Excellent. So, Ryan, NASA has been, some don't have as much background on NASA's open innovation activities. NASA's been utilizing crowdsourcing as a means for problem solving for over a decade now. Is that correct?
Yeah, so NASA started getting into the crowdsourcing space when it was actually the presidential administration at the time in 2005 pushed NASA in that direction. And so since 2005, NASA has been doing crowdsourcing, but at first it was only within the US. And then in 2009, what became my office started some pilot projects, and we were officially formed in 2011. So really it's been over a decade that NASA has been using it. And I just want to add on to something that Jonathan said.
Sure.
Something that we really understand within our office, a huge benefit of crowdsourcing, and maybe all the viewers don't realize this, is the diversity in your backgrounds and experiences. You don't have to be an expert. And that's what's great, is that so often some of the experts are already working on the problem, but they couldn't solve it because they have inherent implicit biases. And so It's the fact that you all have different backgrounds that might just work out for a particular problem. And so even if you don't think you're an expert, you should certainly always push forward your efforts, because usually the winners are people who knew the answer going into it because they just happen to have that right background. So don't focus so much on not knowing every single detail about everything. You can help pretty much no matter what. We're really excited about the solutions we got. They're very diverse, which is what we expect within our NASA Tournament Lab organization, because we know that the power of crowdsourcing is huge.
That's wonderful. I was going to say that you took the words out of my mouth. It's
We're in the same space. We get the same stuff.
Same stuff. Perfectly said. I love it. Okay, so the winners. All right, you guys. We're going to put you guys on the hot seat. No, I'm kidding. We're going to highlight you guys. This is your day. This is your spotlight. So we're going to shine a spotlight on each of you. So there were 5 winners awarded, which I've already mentioned. There was the first, the second, and the third place, best prototype, and most innovative. And we're going to, actually, before we go into that, just to put things into perspective, Jonathan, how many submissions did we receive?
So we received 572 submissions. And I should note, out of those submissions, we were blown away by the number of detailed submissions. When we initially put this challenge out, all we were sort of asking for was sort of 2 or 3 paragraphs of text and 2 images sort of, illustrating how the concept worked. Out of those, 500 some submissions, there were over 50 that were absolutely excellent, that included detailed prototypes or, 20 to 40 page reports with detailed, details on how it worked, and absolutely was incredible to see the response from everyone. As noted, we have 5 winners. We actually added 2 additional winners because there were so many great concepts. In addition, I wanted to also make sure you take a look in the press release at all the honorable mentions too, because we had so many great concepts, that we wanted to highlight, and so much work that everyone put into this. We were just blown away by the response. So first of all, a huge congratulations to the people who are here on this teleconference, right? You guys did an amazing job putting together your concepts, and totally blew apart our wildest dreams for how well this could turn out. So absolutely incredible to everyone here, as well as all those mentioned in the honorable mentions and everyone who participated in this challenge. We were just blown away by your response and your contributions.
Well said. All right, so let's chat a little bit with these guys. So first up, Yousef. So it's going to be the same question to all of you guys. Tell us a bit about the solution that you presented to NASA, and then how did you come up with it?
Okay. First, I would like to say that it wasn't easy at all. It was very tough to come up with a solution that would be very practical and simple to use, and works well with the conditions on Venus. So the main problem, or it was one of the challenges that I met, was designing the holes detection system. It was challenging to design a system that could gauge and feel holes without getting stuck. And I've always admired the TriStar wheels system, and I've always been fond of it and its ability to climb over obstacles and make shopping carts and stuff like that climb stairs easily. But for some reason, I didn't think about that at all during working on the competition. Until one day I saw one of my colleagues playing with a fidget spinner, and that was the moment I knew it's a perfect solution for our case.
Good stuff. Excellent. Now, did you have anything you wanted to screen share or anything, or are you good?
Yeah, so I guess I will screen share my presentation.
Sure.
Okay, so just a minute.
Yeah, and as you get set up, so for each of you guys, take about 3 or 4 minutes, and in your shares, whatever visuals you have ready, you're welcome to share them.
Okay,
Here we go. Absolutely.
Okay. Very briefly, the design breaks the solution into 3 systems. horse detection system, the one using the TriStar wheels. Then we have the rocks detection system. It's simply a structure that's hung from the rover and acts like a bumper. It presses against the stop pin when it hits a rock more than 35 centimeters high. Then finally, you have the slope detection system. It's composed of two inclinometer devices, or devices that can detect the tilt angles of the rover. One of them is responsible for the pitch angles or the forward-backward slopes, and the other is for the side slopes or the roll angles. The three systems work independently, but they all are connected to one lever, one main lever. The orange object here, number 5, that lever, when it's activated or raised, it presses the stop pin at the center of the rover, the gray object, number 1. And of course, the colors are just for illustration. The main material would be titanium 64, but the colors are just for illustration purposes. And the yellow structure or the bumper just pushes the lever by means of cams, and in turn the lever presses the stop pin. The other systems activate the lever by means of bounding cables. There are many bounding cables attached. We have here 4 attached to the lever. When one of them is triggered or dragged, it drags the lever and the lever stops the pin. A TriStar is always resting on 2 wheels and reacting with the ground and the topology and moving up and down with the typology. But when it hits and encounters a rock that it cannot run over, the whole system revolves around it and climbs over it and then rests again on 2 wheels. When it falls in holes and any recess, the connectors holding it extends to a limit that can drag a bounding cable and trigger the lever we have talked about, the stop lever. That is calculated to happen when the hole is more than 35 centimeters deep. Forks extending from the bumpers also protect the system from higher rocks and obstacles that it cannot climb it. Inside one of the inclinometer devices, there is a bob weight or a pendulum that tracks the direction of gravity, and that causes the triggering of the bounding cable when the tilt exceeds 30 degrees. More explanation of that mechanism can be found on the YouTube video of my project. At last, I would like to share with you something. It's the process it's a process I like very much to use when designing. No matter how skilled you are, or how much knowledge you have in engineering or computer skills, it's always a good idea to start experimenting like a kid and doing very simple models and experiments and prototypes to develop your idea more and more before shifting to CAD drawings and involving into details. And that's all. Thank you very much.
Thank you. How cool is that? Great job. Thank you so much for that, Yousef.
You're welcome.
So, all right, who is next in our highlight? So let's go with the team. So Eric and Martin, we'll move it over to you guys. And again, any screen shares that you guys have, we invite you to go ahead and to share that.
Sure.
You want a screen share, or do you want me to?
Yeah, I got it.
Yeah.
Can everyone see that?
Still loading. There you go. We're good.
All right. So in our initial trade studies we did early on, we put a lot of emphasis on using simple, reliable, and well understood mechanisms and materials. And that led us pretty early on to choosing an all mechanical design. But like others have said, the hole detection was definitely the biggest challenge for us early on, because we were having trouble coming up with a simple design that would meet all the requirements, like detecting holes and being able to handle like any kinds of terrain conditions without getting stuck. And then also having a low likelihood of false detections or missing dangerous obstacles that it should have detected. So in the end, we settled on a skid design that basically slides in front of the rover, and the skid is attached to the body of the rover with the 4-bar linkage, which allows it to rise and fall with the terrain while maintaining consistent orientation. So if there's a hole in the path of the rover, the skid will slide down into the hole, and then that 4-bar linkage falls down to a certain angle where it pulls on a cable and causes a trigger event. And then, to avoid getting stuck when backing over obstacles, we have basically a breakaway hinge, which you can see in the bottom right corner, that allows it to more easily pull over obstacles. And that was something that prototyping really helped out with. We actually made a 3D printed model of that mechanism. And so it has the breakaway hinge and then the 4-bar linkage that lets the skid rise and fall. The hole detection, the rock detection was a bit more straightforward for us. We decided to go with a bumper, which is again attached to a 4-bar linkage. And so when the bumper encounters an obstacle like a rock, it rotates that linkage, which again pulls on a cable that causes a trigger event. Another key thing was we decided to mount the bumper assembly on the skid so that a relatively consistent height is maintained between the terrain and the bottom edge of the bumper, so that you have good accuracy in the height of the rocks that you're detecting. Go ahead, Eric.
For the tilt detection mechanism, we ended up going with a pendulum design, and the advantage to that is the terrain underneath the rover doesn't really matter, whether the rover is on an even slope or if it's tilted because the wheels are on top of a couple of rocks. The pendulum always points towards the ground and detects the true angle of the rover and whether it's close to tipping over. So our pendulum design is mounted on a universal joint, meaning it can tilt in any direction. And these cables attached to the crossbars pull on the trigger whenever the pendulum detects an unsafe angle. So for the triggering mechanism, to actually get the input from the sensor to the rover, we went with a spring-loaded mechanism because we had to be able to transmit a small amount of force input from one of the sensors and immediately relay that information back to the rover. So you can kind of think of it like a mouse trap, like a very small movement from the mouse creates an immediate and a large reaction from the trap. The problem with that is that after the mouse trap activates, if you want to use it again, you actually have to walk over to it and reset it. So we basically ended up designing a mouse trap that essentially resets itself. So when one of the sensors detects an obstacle, one of these red cables releases the trigger, and this blue cam rotates clockwise and pushes the pin, which is actually the only form of communication we have with the rover. As that's happening, the mechanism automatically engages with a rotating input shaft from the rover, and that resets the whole thing. And as that's happening, various mechanisms within the contraption reset the trigger and then disengage from the input shaft, so the whole thing is primed and ready to go next time the rover encounters an obstacle.
Yeah, so once we have all those subsystems designed, we have to figure out how we're going to position them on the rover. So the pendulum and the trigger assembly we put in the front center of the rover, and those components are sensitive to wind and dust. So we put them in an enclosure, which is the gray box in the front middle. Then we have 2 hole detectors that are in line with the wheels that protect the wheels from rock or from holes when the rover is driving forward. And then we have 2 hole detectors on the side of the rover that protect the rear wheels when the rover's turning. Then we have 2 bumper assemblies in the front that protect the entire front face of the rover from rocks, and then 2 smaller bumpers on the side that protect the side of the rover when it's turning. So that's a brief overview of how our design works.
Perfect. Thank you so much for sharing that. You know, the amount of the details when you go into all the different components, just so powerful. And like Ryan was saying, it's not like everybody comes from that detailed background. So when you look at the way the mind works, it's pretty amazing. So next up we have Callum. And I know Callum, we are going to do your screen share for you. So
thanks, Carla.
There you go.
So hi everybody. So this is my submission. It's called Direction Biased Obstacle Sensor, or DBOS, because I know how you NASA people love your acronyms. So I went with a slightly different approach. I had a bit of integrated a bit of electronics in it. Actually, we could just go back to this. Oh yeah, that one. So basically, the first slide, if that's okay, Kyle. Thanks. So essentially, it's just a big truss assembly that gets pushed in front of the rover as it drives along, and it's supported by that array of red hole sensor legs that you can see, and there's a rock sensor bumper sticking out the front, and that whole thing can track the ground because it's attached to the rover by a 4-bar main linkage, which is a non-parallel linkage, and there's a tilt sensor up the back in the middle, and when one of those 3 sensing elements detects an obstacle, it'll send an electrical signal back to one of 2 detection pin actuators. So there's 2 there, which gives it the direction biasing. So if it hits a rock on the left, it'll back up and turn right, or if it hits a slope in any direction, it'll turn in the direction of flat ground. If you go to the next slide, Carla. Thank you. So this is just a quick overview of a few of the key systems. So up in the top left, we have the 2 detection pin actuators. So each of those essentially consists of a cam mounted above the detection pin, a spring-loaded cam, and that's held in place by a latch and a electromechanical solenoid. So when one of the 3 sensors sends a signal, it'll essentially release the latch, release the cam, and the cam will rapidly rotate 1 revolution clockwise. Then that little contraption in the middle that you can see is the mechanical input shaft connected to a differential. So that is normally stalled, and when one of the detection pins fires, that gets unstalled, and the input shaft can recharge one of those springs. Next up is the tilt sensor in the top middle. So it's essentially a free hanging pendulum like second place, except it's mounted to a double pivot joint, and there's electrical contacts mounted around. So when it reaches a certain angle, it'll essentially just close a switch and trigger one of those detection pin actuators. But both of those pivots are magnetic dampers. So if the rover falls off a rock or falls into a hole, we won't pick up too many false detections, hopefully. So next up on the far right is the rock and hole sensor detection system. So essentially that green bar on the left is spring loaded forward. When a rock hits it, it pushes it back and provides slack to that little cable there, which allows the little switch hidden in that tube to close and send a signal. And similarly, when one of those legs rotates clockwise, the red legs on the right, it will pull that green bar back and do the same thing. And final part is the non-parallel 4-bar linkage. So in a lot of the designs I came up with, there was an issue where if the rover front wheels went up onto an obstacle, it would see a hole at the far side of the obstacle that wasn't actually there and trigger a false detection. And since the design I ended up going with was supported by the ground, I needed the level of that front section to remain constant regardless of the orientation of the rover. So I designed a non-parallel 4-bar linkage to achieve that. And that's pretty much a brief overview. Thanks for listening.
That's great. Thanks, Callum. You know, for a novice like me, like they all look so far so similar, but yet so slightly different. And it's amazing how you guys all envision the same thing without any collaboration with one another. It's really great to watch. All right, next up we have, let's go with team, best prototype. So Oscars and Christine, what do you guys got for us?
Okay, thank you. I will share some screen. So this is our proposal. It's called dummy sensor. Just a minute.
You know, you're going to have to show us a picture of the baby once you're done, because you just keep talking.
Okay.
Oh.
So as you can see in the picture, AMI sensor has 5 important components for it to work. Firstly, seesaw and mine sensor shaft is in our design acts as one piece. It collects input from all sensors and hands over an output signal to magic pin box, one output signal. Secondly, magic pin box is a device that takes the input from mine sensor shaft and when triggered starts sequence. Pushes a rover sensor pin, releases it and waits while rover is reversing. As a third, there is a rock sensor. When rock sensor collides with obstacle, it turns mine sensor shaft directly. It is designed in maximum allowed height to detect also a large overhanging cliffs. So next part is a slope sensor. It's very, very simple design. It has a very few parts, 2 rotational axes, tilting and rotating. So the idea is that weight will always be in the direction of the ground, and the slope will simply change the angle of the weight and pull this blue pull rod down. That's all. It will be always away from the uphill, and the angle will be proportional to the ground, straight to the ground. So that's very, very, very simple design.
Okay, and the least and the most complicated, as I heard for everyone, was a Hall sensor. So screen share on. Yeah, here you can see, in this picture you can see the evolution of Hall sensor. Altogether we had 5 designs. As the first solution we tested a small wheel with a joint in the vertical column, but the wheel was too small, it would stuck everywhere and the spring mechanism needed a lot of force. In general it just didn't work. Next design was omnidirectional wheel in 70 centimeter diameter. That allowed it to easily climb over high rocks. The good part was that omni wheel design reduced wear when rover was making turn. However, this wheel wasn't able to detect 50 centimeter long holes because it was simply too large. As a next step, we made it smaller, but now it couldn't get out of deep holes or overcome large rocks. We were trying to find solution how to add some assisting elements, but it started to become too complicated as a solution. After this, we understood that simple round wheel doesn't work, so we started to look for different shape. Triangle shape wheel easily can overcome 35 centimeters of height, but there still was a chance that sharp rock can jam or stuck between wheels. So we added a caterpillar track that fills the gap between them. And this idea was finally completing all the tasks necessary. So approximately 10 days before deadline, we went to the workshop and started to make the final stage of prototype.
So there is this wheel. It has not only the ability to overcome these obstacles like large rocks or holes in both the directions, but it has one more ability to steer. so it can move around its shifted axis. So it always be in direction of movement, even when the rover is turning, it will make this movement in direction of path. And because there can be some large rocks in the sensor space inside, which are allowed, and this wheel need to be ready for that and overcome it. So it turns against the obstacle and climbs over. So simple as that.
So yeah, in general that's all, but I would like to quickly also share some pictures, not with the baby, but with prototypes. So this is the process how we were building it.
This was all scrap wood.
Wow.
So this is our workshop, yeah. This is the
very
first,
cool.
the first design.
This was first. It was I knew it that it won't work, and it didn't, and that's all right.
How long did it take you guys to do? Like each
so as
individual?
Christina said, we started like 10 days before the deadline, but
Oh, wow.
but the main body was already done before. We've had the time before. After we found out about your contest, I started to build this body because I knew that it will be useful.
Very impressive.
So yeah, okay, that's it for now. The baby picture is only here.
We'll finish off with the baby picture.
Yeah.
So good stuff. All right, so rounding off, we have one last presentation left. So Matthew, the most innovative. So
okay. So as I mentioned earlier, the name of my concept was called Echoes, which hints a bit about how it functions, and it stands for evaluate cliffs, holes, objects, and slopes. So when I first started working on this, the first parts to be solved in concept at least came quite quickly. A pendulum could feel the rover's inclination, and a push bar would feel rocks simply and reliably. Very similar to the other winners. I first explored around what I knew for the cliffs and holes, mechanisms. I tried various ideas for directly feeling holes, but a good design usually feels elegant, and mine never quite did. They're always too heavy, too complex, and quite often both. Over the past couple of weeks and this webinar so far, I've been fascinated to discover how in their direct feeling designs, other competitors and the other winners have solved these very problems that ultimately defeated me. So eventually, inspiration struck for something entirely different, sonar. So if we could have the next slide, please, Kyla. So we think of sonar as being used in liquids, but famously bats use it in air to very great effect. And with Venus air being so much thicker than Earth's, it would work even better there. Because mechanics of my area and electronics on Venus so limited, I set about trying to design a fully mechanical sonar. I'm quite fond of the expression extraordinary claims require extraordinary evidence. And this solution would be unusual, so whoever heard of a mechanical sonar? And so I hit the books, learning what I didn't already know to be able to calculate the performance of all the core functions of the sensor, ensuring as best I could that it was going to be viable. The submission needed to have all the bases covered if it was going to have any chance. So the design steadily took shape. Can we have the next slide, please, Callum? A sounder like a drum or a clave would make a sharp sound pulse, which would be directed at a small spot on the ground. If the sensor was not over a cliff, an echo would reflect off the ground and hit a receiver diaphragm whose reaction would be mechanically felt. Echoes didn't need to determine the precise feature depth, only if it exceeded a specified maximum. For the height that I was putting my sensor, I calculated that if an echo returned within 47.4 milliseconds after sounding, the ground level was fine. An echo taking longer than that, or no echo at all, indicated a deeper feature, which may also be a problem. But what would you do about that? That only tells you about one very small spot, and as we've discussed, the wheels can overcome very wide holes. So I designed a mechanical counting system. if two adjacent sensors both found 3 consecutive points that were too deep, Echoes had found a hole that was impassable for the wheels, or it was looking down a cliff face. And so when the sonar, the pendulum, or the push bar were triggered for any reason, they would pull a Bowden cable, which would release the pin to command the rover's avoidance maneuver. So I seek to be always learning, and exploring hell was a very unusually fun way of learning. It furthered my knowledge of areas like material selection and engineering for high temperature environments, which is going to help me in my day job. And most significantly, before starting this, I only really knew the very basic principles of sonar and not much more about acoustics generally. My knowledge of them is now deeper, but I still only really scratched the surface. There's a lot more to learn. I'd just like to finish by saying my whole exploring hell experience has been unvaryingly positive. I'll quickly take this opportunity to thank Jonathan, Ryan, Kyla, Kai, Christian, and the rest of the teams at NASA, JPL, and HeroX for creating and conducting this inspiring challenge, and to the other competitors for engaging in interaction always so positively. My congratulations to the other winners with us right now, all the other honourable mentions, and everyone else that entered the challenge, stretching yourselves to devise solutions to a really unique problem. Even if you didn't ultimately get as far as a finished entry, I'm certain that you learned lots, and the experience will help you in the next challenge. I'll be watching with interest how the automaton rover for extreme environments develops and proceeds from here. And in years to come, I'd dearly love to see a mission based on this concept fly. Thank you.
Wonderful. Very, very well said. Very well said. So great shares, you guys, each and every one of you. And like I said, although there's obviously a common thread, there has to be, but each and one of you approach it just slightly differently. Just really well done. And thank you so much for taking the time to then put together these presentations and socializing them and sharing them with us, because it's the spirit and the passion that we hear when you guys share and talk. That's what's most inspiring. So, you know, Jonathan and Ryan, I mean, hearing a little bit of the soft facts and the people behind the solutions now, I mean, any final comments?
So I should note that over the last 2 days, I've had the wonderful opportunity to sit down with a half hour of each of these finalists, or each of the winners here, and it's been incredible to talk with them about the design, how the design has evolved, and yeah. Well, I sort of cheated before this webinar, but yeah, like I said, it's just really incredible. The you know, winners have totally blown us away, but in general, everyone who submitted to this challenge, really amazing work to everyone. Huge congratulations to the winners. This was the competition, and this was tough. It was so incredibly hard getting down from the 15 or so that we had as honorable mentions down to the final, first, second, third place and best prototype and most innovative challenge. As noted, we added those 2 extra additional categories at the end just because there were so many great entries that we wanted to celebrate and recognize you for your incredible work and for all the great work that you did. So I think I'd like to say thank you everyone for contributing your ideas and for really giving us a successful approach in technology forward, where I think if, you know, we would have tried to come up with this on our own, we would have run into a number of those problems that you guys detected, and you've found a lot of the landmines for us, things that we probably wouldn't have detected until much later on in the concept. So having, you know, a number of people work this in parallel has really helped us to understand what are the real problems and find solutions and workarounds for each of those issues. The end solution, as I noted, right, will be, you know, moving forward with one of these concepts in our future proposals. I should note, it probably won't just be one concept, though. It'll probably take, it'll take bits and pieces from each of these winning concepts that you see, combining them together to that, you know, to a solution that sort of addresses all sort of the edge cases and corner issues that you sort of heard some of the different teams and individuals work through. So once again, absolutely incredible work, and thank you all for contributing. Thank you also to everyone who participated in the forum. I know that was really helpful to a number of people in figuring out what were some of those challenges and different ideas and solutions for coming around it. It was amazing to see, even though this was a competition, the very collaborative nature that occurred in the forum of everybody working together towards a solution. And I look forward to many future successful prize challenges in the future.
Wonderful. You know, it's one of the things that you shared, we hear that so often, is we were blown away by the results. And it's what we live for at HeroX to hear, because we work so closely with, you know, all of our sponsors, and we're so hugely committed to your guys' success. So when you actually walk away and are able to say that, that's literally music to my ears. And I know I speak for both Kyla and Christian. Ryan, anything else to add to Jonathan's share?
Sure. I want to first start by thanking Jonathan. We have lots of different challenge owners and project owners when we reach out and do crowdsourcing, and they understand what we're doing and they work with what we're doing at varying levels. And Jonathan was so engaged. He was the perfect challenge owner for this, and he was so committed to helping the crowd get the solutions and understand what they need, while also, you know, not giving them the answers that he had in his mind, because you don't want his biases to go in. And man, he just put forth so much effort. So I really appreciate Jonathan working hard and enabling you all to help NASA. Now, saying that, Jonathan and I have been very fortunate to have circumstances in our life where with hard work, we got to work for NASA. Like, how cool is that? And just like any other job, though, it can start to feel like a job after a while, believe it or not. And it is really, really nice to hear how excited you all are to have an opportunity to work for NASA, because we know it's a brand that's known worldwide. You know, NASA is here to help humans explore the cosmos. Like, how cool is that? And so we love within the NASA Tournament Lab that we can utilize you all to get us good solutions, but we also love that we can help you, you know, impact NASA and thus impact humanity. So more challenges will continue to come. HeroX already has other ones like Lunar Loo. You're going to see more coming from NASA Tournament Lab all the time on platforms like HeroX and others. So look us up if you're not familiar with NASA Tournament Lab, and keep giving us your great solutions.
Ryan keeps us very busy. I'm just saying, you'll be seeing a lot more projects coming. So if you found this fun, there's so much more there. Christian, I'm going to come to you. So, you know, you've heard all of the stories, you've seen the solutions, and I know, you know, Christian reached out to me and he said, is it okay that I join? I want to personally come and congratulate and thank the winners. So floor is yours.
Awesome, thanks, Cal. Yeah, no, that was great to see those solutions. I'm super excited about them. I've always, since I was a child, I've always been fascinated by Venus and, you know, space in general. But Venus is such a mystery. We know so much little about it, and there's so many secrets yet to uncover about it that I think it's going to be amazing if we can send a mission there. You know, I think that, like, we live in a society that's really really celebrates innovation, loves technology, but I'm always amazed at how everybody talks about the gadget or the invention, you know, in other words, the tools, and they forget about the tool makers. You know, I've checked, and there's really only one source of innovation, and that's human beings. And it's funny how quickly people skip past them. You know, I think innovation is a human activity. It's a fundamental element of our nature that makes us different than all the other species. Our ability to create, ability to make tools, our ability to come up with an idea and then make it a real thing. It always amazes me to see it happen, and I'm just really proud of what I've seen today. And I'm really looking forward to a future where, you know, innovation just becomes more democratized and merit-based, and more companies realize that ideas can come from anywhere. And we have 7.7 billion people on this planet. They're all geniuses at something. And so let's, you know, let's really create a world where people can find their hero's journey and do some amazing work. And so good luck to everybody here. I know you're all going to be richer from your experience here and the street cred that you gain from, you know, having been a winning innovator for NASA, for freaking NASA. I think it's awesome.
Wonderful. Very well said. So we're coming up to the close of our discussion for today. I wanted to take a minute and just reflect. As a HeroXer, when we look at our community of solvers, there's over 175 different countries represented on our platform. There's a lot of you. I mean, it's mind-blowing, the depth of the reach of the platform. But the cool thing is there's so many of you from so many different walks of life. And I think that's what makes the HeroX platform and community so unique. Genius can live anywhere, as Christian has alluded to. And in looking at the 7 of you, that is absolutely true. So, once again, on behalf of the NASA and the HeroX teams, congratulations to all of you. Well done. And it was just so amazing to see your presentations and how compelling it was to hear some of the stories and some of the passion behind the journey that you actually took. To our guests, all of you guys, we really appreciate you taking the time out of your busy schedules today. For our listeners, I'll leave you guys with a challenge. So if you haven't already done so, join our crowd of solvers like these 7 amazing individuals, or challenge the crowd and find your next breakthrough idea just like NASA did. Be inspired and get inspired. And with that, I'd like to thank you all for your time today. Please stay safe, and depending on where you are in the world, have a wonderful morning, afternoon, or evening. Thank you so much, everybody.